Okay, let's start. So today our topic will be the same. We are continuing that topic, linear homogeneous PDE with constant coefficient. But as in our last video, we have seen that the right hand side was non-zero. It was some function of x plus by. We will discuss about some trigonometric function, exponential function, or maybe some general function of x plus by type. In this video, we will be discussing our case number 2 when the right hand side is particularly of this type when x to the power m multiplied by y to the power n. Let me write it. Case 2. Case 2. If the right hand side of our equation number A, we called that function gxy, is equal to x to the power m and y to the power n, right? Then our particular solution Ps is equal to 1 over f d dash operated on x to the power m y to the power n can be written as f d dash whole inverse x to the power m y to the power n, right? And expanding f d comma d dash the power minus 1 in ascending powers of d over d dash or d dash over d will give the closed form of Ps, right? So finding particular solution for x to the power m and y to the power n, what do? We just take this operator like this, means the inverse power of this, as we have discussed in our last lecture that it behaves as a single entity and can be taken anywhere, right? So f d dash can be taken in the numerator with the power minus 1, and after writing this way, then I have to expand this f d dash whole inverse in ascending powers of d by d dash or d dash by d, whichever will be suitable. That will depend on the numerical, and that will give the closed form of Ps. What do you I mean by closed form? Closed form means not in expanded form. We need a particular solution in a closed form, not in an infinite series, right? If by applying these two expansions either in d by d dash powers or d dash by d powers, I am getting an expanded form of function, then I will reject that expansion. That means that we will select these out of these two, that expansion for which the output, means the Ps particular solution, will be some closed form function, right? And by saying so that it can be expanded in powers of d by d dash and d dash by d, maybe sometimes that you are allowed to expand in powers of d by d dash and d dash by d both ways, then we'll get two particular solutions. And this is a key point to understand that fact that the particular solution of a partial differential equation is not unique, especially for the case when the right hand side is a function of this nature, right? And then particular solution is not unique. One given by the expansion in powers of d by d dash, and the other may be given by in powers of expansion in the powers of d dash by d, right? We will see that in our examples. So you remember this remark that particular solution for a PDE is not unique, right? Okay. Taking example number 1. Right, and one more thing that when you expand this f d dash in ascending powers of d by d dash or d dash by d, we do not take care too much about the convergence criteria. Means when you apply the expansion of this type 1 plus x whole to the power n, then we have some expansion 1 plus nx into n minus 1 by 2 factorial x square and so on. but there is a condition that mod of x should be less than 1, right? But that condition is not required for this, right? So this is not a real number, right? It is just a single entity and it is behaving good, and the reason is still not known to me. Okay, so moving to question number 1, example number 1. Let me take the example which we did in our last video, that was d to the power 4 plus d dash to the power 4, if I am not mistaken. Z is equal to, the right hand side was x, maybe the example number 5 or 6 of our last video. Okay, so solution. Should I write the complementary function directly, because I did that in last video. Then I am writing that CF directly. It was, I think, f1 y plus m1x plus f2 y plus m2x plus f3 y plus m3x plus f4 y plus m4x, and where f1, f2, f3, f4 are arbitrary functions, and m1 was given by first quadrant 1 by root 2 plus eta by root 2, m2 that was in second quadrant, means x negative and y positive, m3 that was in third quadrant, x and y both negative, and m4 was x positive and y negative, right? These were our m1, m2, m3, m4. You can, for detail, you can refer to our last video. Okay, so this is our CF, and now going on to particular solution. Is given by 1 upon d to the power 4 plus d dash to the power 4, and here we have x. Now there are two ways to evaluate this. Either you want expansion in the powers of d dash by d, or in powers of d upon d dash, right? And that is giving rise to its two different particular solutions. I will do them separately. Let me take d to the power 4 common, or should I take d dash, no, d to the power 4 common, right? Okay, so taking 1 upon d to the power 4 common, and inside I will have 1 plus d dash to the power 4 by d to the power 4, and here I have x. Then it will be brought up in the numerator with the power minus 1. It will become 1 upon d to the power 4 and 1 plus d dash to the power 4 and d to the power 4 x, right? And here we have power minus 1. Now you should remember the formula of 1 plus, let it be z, 1 plus z whole to the power minus 1, and that formula is 1 minus z plus z square minus z cube, means the power of z goes on increasing and the sign fluctuates, plus minus plus minus. Okay, then 1 upon d to the power 4, 1 minus this z, okay, and then plus square of this term, that will be d dash 4 d 4 whole square, right? And so on. The sign goes alternate, plus minus plus minus, and the power goes on increasing, this power 0, power 1, so on, like this. Okay, I should mention the formula here. Here I have x, and I have used the formula hash 1 plus z to the power minus 1, 1 minus z plus z square minus z cube, so on. Okay, now take this x inside, x will appear here, then x will go here and here, right? It will give me 1 upon d to the power 4, and x multiplied by 1 will give x, but x, when x is taken here, then obviously d dash means the differentiation with respect to y, but here I have only x, and when x goes here, then differentiation of x with respect to y 4 times, it will be 0 obviously. Okay, then all terms will be 0, right? And this is a very good indication why this expansion is useful, because a polynomial means x to the power n maybe, differentiating n times will give a constant, and differentiating more than n will give 0. And that is the key point then, that why we always obtain a closed form here. This is not a infinite expansion. However, I applied that infinite expansion formula, but at last I am getting a single term, means a closed form of the solution. That is what we needed, right? And then 1 by d to the power 4, then x, and 1 upon d, as d stands for differentiation with respect to x, then 1 upon d stands for integration with respect to x, right? And 1 by d to the power 4 means integrating it 4 times, right? So integrating it 4 times will give x to the power 5 upon 5 factorial, means 120, right? And then we can write the complete solution. Z is equal to Cf plus Pi. You will write it yourself. Okay. And indeed, that's the same answer as we obtained in our last video. The same question has been done there, and that was the same answer, right? Okay. And let me try to do this another way. Instead of taking a common d to the power 4, if I take d dash to the power 4 common from the denominator, then what will be my answer? Let me write it alternate to find this PS. Okay, PS equal to, I will take d dash to the power 4 common this time, 1 upon d dash to the power 4, 1 plus d to the power 4 upon d dash to the power 4, and here I have x. Now applying the same argument as I did here, and it will be taken in the power minus 1, then it will be expanded in powers of d by 4 and d dash to the power 4 here. Then ultimately I will be getting something like this, 1 upon d dash to the power 4 and then 1, right? And this will be minus, and so on. And then putting this x here, I will write that 1 minus d to the power 4, d dash to the power 4, and plus etc. Those terms are not needed actually. And taking this x here inside, that will be x. And d4 means differentiation of x. D stands for differentiation of x with respect to x, and differentiating it 4 times will give 0. So I will only have x ultimately, 1 upon d dash to the power 4 x. And here 1 upon d dash stands for integration, but with respect to y this time, right? And integration with respect to y 4 times, because 4 is appearing here. This term integration 4 times with respect to y will give once it will give y, once, then y square by 2, then y cube by 6, then y to the power 4 upon 4 factorial, it will be 24. In that case, this is the particular solution, and see the difference. This is x to the power 5, this is xy whole to the power, xy to the power 4 by 124. And these particular solutions are indeed the different particular solutions, but they both satisfy this equation. Yes, right? You will try it yourself. I mean, I should write it here. For these two, this as well as this, they both satisfy our equation, that equation, d to the power 4 plus d dash to the power 4, then z equal to x. You just plug in this value here, means differentiate it 4 times and plug it here, that you will get x equal to x. Or you can plug this value here, you will get x equal to x, means they both are correct, right? But they both are different. And that was our point, that particular solution of a PDE is a non-unique value. Okay. Next question. Example number 2. Okay, right. Let me solve d square minus 5d d dash plus 4d dash square, right? And z is equal to x square y, right? And in this problem, right hand side is consisting of x as well as y. Okay. then its complementary function will be, its factors will be -4 and -1. Yeah, right. Okay. Then it will be like complementary function is equal to f1 y minus x and then f2 y minus 4x. I'm writing it directly. There f1 and f2 are arbitrary functions. I'm not writing that again and again. Okay. And then particular solution is equal to 1 over d square minus 5d d dash plus 4d dash square, and here we have x square y. Right. Okay. So again, there are two ways to do it. Either you take this common 4d d dash square, right, or you take d square common. Okay. If you take d square common, then the expansion will be in powers of d dash by d, right, and that will be easy, I think so, because d in the expansion in the powers of d dash by d indicates that you have to perform differentiation with respect to y, because on the numerator we have d dash. If I take this common d square, then here I will be getting 4d dash square upon d square. In the numerator I will be having d dash, and the expansion, all the expansion terms will be containing d dash by d, means d dash will be appearing in the numerator, right, means you have to perform integration with respect to y first, and luckily the power of y is less, means the job will be done too easily, right, in spite of taking d dash square common. If I take d dash square common, the expansion will be containing the powers of d by d upon d dash, and the differentiation will be performed with respect to x, and x to the power is 2, means I have to perform differentiation more as compared to the case when d dash by d terms are contained in the expansion, right. So you see this point, whichever is easy or whichever you prefer, you can do that. Okay, however both are correct. So I am taking common 1 upon d square, right, and in bracket I will have 1 minus 5, I think, d dash upon d, and plus 4 d dash square over d square, right. Okay, taking d square common will produce this, and if I take this minus common, then I have to put minus here, and this is written in this way. Okay, and here I will have x square y, right, and then taking it over the numerator and then expanding it, I will get 1 by d square 1, then plus 5 d dash. This time the formula will be 1 minus z whole to the power minus 1. I will write that formula, 1 plus 5 d dash by d minus 4 d dash square over d square, that is my first term, z, and then it's square, but that is not needed indeed, 5 d dash by d minus 4 d dash square by d square whole square, so on, and here I have x square y, and the expansion I used is 1 minus z whole to the power minus 1 equal to 1 plus z square, means all terms are positive, all terms of the expansions are positive, right. And now taking terms like let me take this term here, x square y will be taken here, x square y plus then 5d dash by d operated on x square y, and if I write this 4d dash square, but it is containing the term d dash square, means differentiation will be performed twice with respect to y, but that will give me 0 because y is having power 1 only, right. So no need to write this term. Even the square term, if you open the square, you will get, in every term you will get at least d dash square, and there is no point writing them all because I have only y to the power 1, and there is an advantage I have got if I expand in the powers of d dash by d, right. That's it for it. Here I will have, okay, that is it, right, 1 upon d square x square y, and the differentiation of this term with respect to y will give me x square only, 5 1 upon d x square, right? And then what is 1 upon d? 1 upon d stands for integration with respect to x. Perform its integration with respect to x. That will be x cubed by 3. Ultimately, I am writing the result directly, x cubed by 3. So this will be my value. Now see this operator, 1 upon d square is still standing here, and you have to perform integration with respect to x twice. So integrate each term twice with respect to x. So integration of this term with respect to x twice will give me x to the power 4 upon 12, yeah, and y. And integrating this term will give me x to the power 5 upon 20 to 60. Okay, then it will give me something like 5 cancel 12, right? So this is the final result. I think we can take common, x to the power 4 by 12 can be taken common, right? X to the power 4 by 12, and you have y plus x. This is your particular solution, right? And if you take d dash common, then another particular solution will be obtained. So you need to find only one of them, that's fine. And the final solution can be written as a sum of complementary function and particular solution, right? Okay. Now, going to another example, example number 3. Let me take it d minus d square, d dash minus 2d d dash square, and then plus d dash square, then it will become d dash cube, and here I have z, and here suppose I have 1 upon x square, right? Here the x to the power is minus 2, you can write that x to the power is minus 2, negative exponent of x. So solution, then writing its auxiliary equation. No. Auxiliary equation method should not be used here, because if I write the auxiliary equation, then I will be putting d is equal to small m and d dash equal to 1. In that case, I will be getting m square minus 2m plus 1, and unfortunately the degree of my polynomial m square minus 2m plus 1 will be 2. Quadratic polynomial will be obtained, and see the order of this PDE, it is 3. So that restricts me to use that method. So I have to perform the factorization, linear factorization of this in this way only. So taking d dash common, that's clear. I will have d square minus 2d d dash plus d dash square, and then operated on z, right, equal to 0. Let me take it 0. Let, right, you cannot write auxiliary equation. Okay. Then it will be d dash, and it will become d minus d dash whole square operated on z equal to 0. Okay. Okay, right, that's fine. And you can write it as 0d plus 1d dash d minus d dash, this is whole square, or you can write it twice, equal to 0. Now try to write the complementary function using this. Therefore complementary function will become, for this you write f1 0y plus x, then I am writing it x, this 0y plus x, and for this thing f2 y minus x. No, the sign is changed, I think. Yes, the sign gets reversed. Y plus x, and here since the power is 2, means the solution, the f3 y plus x for repeated factors. This will be the complementary function. F1, F1, F2, and F3 are arbitrary, right? And now moving on to particular solution, that is very interesting. And particular solution, 1 upon that is 1 upon x squared. Should I write this or this? I think this will be much better, right? D dash d minus d dash whole square, and here I have 1 upon x square, right? Okay, 1 upon x square. Now, as we have seen in our last questions, that we were free to expand either in powers of d by d dash or in powers of d dash by d, but this example is restricting us to expand this in powers of, I think, d by d dash. Yes, there's a big restriction here. I cannot expand in powers of d by d dash, right? And I will tell you the reason. First, there are two possibilities. Either you take common d or you take common d dash, right? If you take common d dash, okay, because as I said earlier that you are free to expand in powers of d by d dash or d dash by d. So suppose you choose this d dash, then d dash square will be taken out here, and in bracket you will have d upon d dash, means the expansion will be containing the term like d by d dash, term like this. Okay, these terms will be this kind of terms, okay, so on, and outside you have this function, see this, and this will be I think 1, maybe 1, okay, if you take d dash common, right? But see this, if you bring this 1 upon x square here, that will be 1 upon x square, that is fine. If you bring this 1 upon x square here, then differentiation of 1 upon x square will be something that will be minus 2 upon x cube, and the double differentiation of 1 upon x square is something obviously, and that series will not stop, right? And that will be a non-terminating infinite series, and that is the thing we don't want, right? Because we need a closed form of solution, we don't need a solution in the expanded form, right? So in order to avoid this situation, you have to avoid taking common d dash, right? So we have only one choice here, we are restricted, so the common will be only d, right? And that will work definitely. I think you all understand the reason why can't we take common this d dash here, right? Okay, so 1 upon d dash, and obviously this has to be taken common, d square will be taken common, d square, and in bracket I will have 1 minus d dash over d, and here I have square 1 upon x square, and bringing this square term in the numerator with the power will become minus 2 here. I will get 1 upon d dash upon d square 1 minus d dash by d whole to the power minus 2 1 upon x square. I will put a mark here, right? Caution, right? Do not take d dash common, and why? You can find the reason by yourself why, right? Okay, so average here, and expanding this, and you must know the formula of 1 minus z whole to the power minus 2, right? And I will write the formula 1 upon d dash d square, and using the formula that is 1 plus 2 times of this z, and then 3 times of z square, and then 4 times of z cube, and so on, right? 1 upon x square, I should mention the formula here as 1 minus z whole to the power minus 2, and formula is 1 plus 2z plus 3z square plus 4z cube, and so on, right? And see that the differentiation will be performed with respect to d dash, means with respect to y, and definitely the differential of this with respect to y is 0, and that is the advantage we have got in expanding by expanding powers of d dash by d. And let me take all these 1 upon x square here, I will get something like 1 upon d dash d square, and 1 upon x square taken here, I will have only 1 upon x square, all the terms will be 0, and now integrate with respect to x twice, and then integrate with respect to y once. Okay, let me rub it. Is equal to 1 over d dash, and integration of 1 upon x square, once it will be minus 1 by x, and the second time it will be minus log x. So ultimately I will be getting minus log x, integrating it twice. You can do it by yourself, and then integrating this with respect to y, I will get minus y log x. Okay, right? So this is the particular solution, and the full solution is complete solution is given by z equal to cf plus pi is complete solution, right? And one more thing to notice here, that you can apply the commutative property here, because as I said, that d can be taken in the denominator, it can be multiplied with the d dash, or can be switched using that commutative law. Means you can switch these. So in spite of writing d dash here, you can write d dash here, right? If you write d dash here, right, then you have to perform integration with respect to y first, and that will produce a y here. 1 upon d dash of this thing will be y upon x square, and then after that you will follow the expansion in terms of d dash by d, as I did, right? I think the answer will be same. I don't know whatever will be the answer, but you should perform that also, right? At this point, you have some alternate way to solve this, right? PS. Okay, that's the homework. And okay, so we have done 3 questions on this, and I don't think that now new examples will be needed. If I write it here y, means the right hand side becomes y, then again the same theory will be applied, right? Okay. So let us move to another topic, that is what happens when this becomes 0. So far we have done the numericals when this denominator term doesn't go to 0, right? Definitely in this case we can't obtain 0 because we are using the expansion here. 0 is not allowed in the denominator here because we are relying on the expansion rather than substituting these value of a and b, as we did in our last video. When the right hand side was phi of ax plus by, we just replace the d by small a and d dash by small b, and when we perform the integration n times, right? And in that case there is always a danger to get 0 in the denominator, right? So we are discussing that case, that we call it exceptional case, when we get denominator is equal to 0, right? Okay, so I have to rub it whole. Okay, so now we are discussing about the exceptional cases. Exceptional case. And what is that exceptional case? That first I should write what we have done so far. So far we have done particular solution, means 1 upon f of d dash, and here I had function like phi of x plus by, and we use this formula. I think d was replaced by a and d dash was replaced by b, f a comma b, and I integrated it n times, right? N times, and here I have phi u du du, obviously n times. So we have done this case in the last video, and the condition was provided we mentioned this condition, provided f of a comma b is not equal to 0. Means this formula is valid if and only if the fab doesn't go to 0, right? So, and we have done in this video that and PS for the case 1 upon f d dash, when the right hand side is some x to the power m and y to the power n type function, then we just bring this f d dash in -1, and then we allow us to expand it using binomial expansion, and so on, right? And so on. So far we have done these 2 cases, right? But especially for this case, because I have to write f1 upon fab here, and there is always a danger to get fab equal to 0, and that will be discussed in this part of the video. And leaving this here, because here for this case we don't put ab here, we just apply binomial expansion, so this is fine, right? So exceptional case for this case, when the right hand side is phi of ax plus by, right? I am writing that. In case f of ab equal to 0 for this case, then this method, above method fills, above method or formula fills, right? Formula fills, right? Then we have to derive some new method to evaluate the particular solution in this case, right? So first I will write that formula and then I will prove it. Okay. Then the above method fails and we use this new formula, that is particular solution is equal to 1 upon, see this, f d dash, and here I have phi ax plus by, but this time f of a comma b is equal to 0. And if I say that this fab is equal to 0, then definitely this fa comma will be of the form this type, see, b d minus a d dash. Because if you put d is equal to small a and d dash equal to small b, you will get 0 in the denominator, and that is the case we are discussing about. Means you need 0 in the denominator, right? Then the denominator will be of this form. And why I have written a linear factor, why it is not a quadratic factor or cubic factor? Because I know that this fdd dash can always be factorized as a product of linear factors, as we discussed in the first part of this topic, right? So I have written just only one linear factor, and it may be the case that there are k linear factors or n linear factors. The worst case is that there are n linear factors, all of them going to 0. What is n? N is the order of this PDE, right? And this all n factors go to 0. That is the worst case, and we are discussing the formula for that worst case. Okay, and here I have written this power as small n. Okay, in that case the formula for evaluation becomes x to the power n and phi ax plus by, and it becomes n factorial b to the power n, right? This is the formula we will be using in the numericals. First we'll prove this formula, how it appeared. I will put a box on it, and this is the formula for the case if f of a comma b is equal to 0. We are discussing this case, fab is equal to 0. Then this will be the formula we will be using. We will leave this formula, reject this formula. Okay, now proof of this formula. See, proof. Right. In order to prove this formula, I should write a PDE of this form only. I mean b d minus a d dash, and then here I have z is equal to phi of ax plus by. Obviously the right hand side is phi of ax plus by. I have to use this formula. Okay, now see what happens. If I solve this, obviously this is a first order and first degree equation. If you remember the Lagrange's form equation, that is small p into capital P plus small q into capital Q equal to capital R, there is that form, and that will become, if I take this z here, this will become b, and then z dz becomes a small p, then a, then it d dash z becomes a small q equal to phi of this ax plus by, right? And this is Lagrange's form of equation, as we discussed in some of our previous videos. Lagrange's form, right? And how we solve it? We write Lagrange's subsidiary equation. Those are given by dx upon capital P, that is b, dy upon capital Q, that is minus a, and dz upon this phi ax plus by. And how we solve them? We take first two ratios and then we solve them, and then we take another two ratios and integrate them. Taking first two ratios, I am not writing in detail. I am taking these two ratios and performing integration both sides. I will get minus a dx is equal to b dy plus some constant c1, and that will give me ax plus by equal to c1, and c1 is the constant of integration, right? And let me take it equation number 1, right? Or should I write it as equation number 1, this equation? Equation number 1, this is my equation number 2. Okay. And then if I take the first and third ratio, taking first and third ratios, then I will perform integration that, and ax plus by is luckily c1. I have tried that. Dx upon b is equal to dz upon phi of c1, and that is all we wanted to perform the integration, because now this becomes a constant and integration with respect to z becomes easy, and integration on both sides will have appear here b dz, or this will go here, and gives implies z equal to x times phi of c1 and some another constant c2, because every time you integrate you will get a new constant, right? But remember that we are finding the particular solution, we are not finding the general solution, we are finding particular solution, and we know that a particular solution does not contain any arbitrary constant. So choosing this constant equal to 0, I am choosing this constant to 0. We choose this way, okay? And why we are choosing this? Because we need particular solution, right? So I am taking C2 tending to 0, means C2 equal to 0. It can be arbitrary constant, but this time we are selecting it to be 0, right? Then okay, then it will become z equal to, then from first and second, no sorry, second and third, this is my third equation, then second and third gives the solution z is equal to x times, it is b, here we will have b, okay, x by b and phi of c1, and what is c1? Ax plus by, okay. So this is the solution for this equation number 1, means this Lagrange's form equation, okay. Now what should I do? Okay, right, see this formula, it has power n and I have solved power 1, so I have to perform it n times. So this is just once, I mean the value of z will be given from using equation number 1, I will have the value of z from 1, it will be 1 upon bd minus a d dash and phi of ax plus by equal to this x by b phi ax plus by. Look what we have got, almost we have reached our formula, but the one difference is that here we have n and here we have 1, so I have to generalize this for n, means operating it twice or directly finding it for m. Then my target is this term, I am writing that bd minus a d dash n phi ax plus by can be written as 1 upon bd minus a d dash n minus 1 and 1 upon bd minus a d dash, right, because this will produce addition of these exponents will give this phi of ax plus by, that's fine, okay. Now using this result, it should be equation number 4, right, use this result, I will get 1 upon b d minus a d dash, and here I have n minus 1, and here the value using equation number 4 will be x upon b phi ax plus by. I should write using equation number 4, right. And now I have to find 1 upon b d minus a d dash, and should I split this power again, n minus 2 and 1 upon b d minus a d dash to the power 1, and operated on this x phi, and where is my b, small b, take this b outside, okay, or should I write it here, b, okay, phi ax plus by, right. But again I am trying to use this equation number 4, but unfortunately the difference is that, see this value and this term, here I don't have x, this time I am x here, right, and that is creating the problem, and to compensate this x I have to do some modification on the proof. Should I write it here capital X to the power r? Yeah, x to the power r, x to the power r, because that will balance our calculation. X to the power r, let me write it, x to the power r, and here I will have x to the power r, where, okay, here, x to the power r, and on integration will become x to the power r plus 1, x to the power r plus 1 upon b times r plus 1. Okay, right, this is fine. This is x to the power r plus 1 and b times r plus 1. We are getting some general result. Okay, and this will be x to the power r plus 1 into b times r plus 1, correct? And then this n is broken in this way, right? That's fine. And this value, using this value from equation number 1. But if I need to use equation number 1, see here we have x to the power 0, right? And if I want to use this equation number 4, I have to put assume r equal to 0. So for r equal to 0, I have x to the power 1. Okay, then it is fine, x to the power 1. I have to mention that using 4 with r equal to 0. R equal to 0, right? Now it's fine. Okay, then we'll get this, right? Now again use equation number 4. There is a point I wanted to use, because I need x. I'm having x here. I wanted to use a formula which is having x to the power something, right? Okay, now here I have x to the power 1, and to use this equation number 4 again and again repeatedly, I will have r equal to 1 to use this, right? And in that case I will have x square by b. Okay, this is fine. So 1 upon b d minus a d dash to the power n minus 2, and operated on this b will play no role. It should I write it outside, 1 by b. Okay, 1 by b, right? Okay. Applying again formula number equation number 4 for particularly r equal to 1, I will get x square over b, and should I write it b square? That will be easy to generalize. Okay, and r plus 1 means 1 plus 1 2, or should I write it 2 factorial? 2 factorial, because in the first term I was getting only 1 or 1 factorial. I'm going to generalize it, right? And phi of ax plus by, I have to mention again, using equation number 1 with r equal to 1. So applying this process repeatedly n times, ultimately I will be getting x to the power n, b to the power n into n factorial, right? Because this operator has to be operated n times. Okay, so dash dash equal to, I'll get x to the power n upon b to the power n factorial, and phi of ax plus by, using equation number 4 repeatedly, right? So this is the result we wanted to prove. You see this result is the same, n factorial b to the power n, that's the same, and the numericals will be done even in our next video. Thank you.